Hello everyone, I'm Gerald, joined by my colleague Yatpang and Yan. So today we'll talk about how we transform our private cloud into a planet-scale computer by abstracting away regions with global service placer. Next, let's look at the evolution of service deployment. In 2011, our services were small and had single cluster deployment. Our private cloud offered cluster as a computer abstraction. In 2012 and 13, our services grew and had multi-cluster deployment. To simplify the management, our cloud provider up-level abstraction to the center region as a computer. So we transform the multi-cluster deployment into single region deployment, which were much easier to manage. And after 2015, our service continued to grow and they start to span across multiple regions. So the state of the practice is that the service operators are managing multiple regional deployments on their own. But let me share the complexity of this task. Stateful services are commonly multi-tenancy, which hosts very diverse tenants with different SLOs. And service deployment need to make sure all these different SLOs are satisfied. And second, the types, the availability, and cost of hardware can vary drastically across regions, which makes service deployment harder. And third, at Meta, we require services to tolerate single region failures. To provide all these capabilities, service operators need to interact with multiple cloud components, such as capacity management system, job management system, shard management system, and the traffic routing system. So currently, two approaches are followed. The first approach is to manually or use very basic script to stitch together multiple regions. This is ad hoc and not reliable typically. It only works for very simple services. The second approach is for large teams to build their own domain-specific solutions. So as Meta continues to grow, the number and heterogeneity of our data center regions continue to grow. Therefore, the current practice is not sustainable anymore. For the rest of our talk, so we will talk about our vision and the solution to the problem, followed by a case study of AI inference. And we'll wrap up the talk by sharing our takeaways and future work. Next, I'll hand over to Yatpang to talk about the vision and the solution.
Thanks, Gerald. As mentioned, service deployment boundaries have been evolving from single region to multi-region deployments, and cloud providers have continued to treat data center regions as the unit of computer. As we continue to evolve into the future, there's a need here to have a better abstraction. To achieve this, our vision to transform the cloud into a planet-scale computer with regions abstracted away. To do that, we built our generic solution, which is Global Service Placer, or GSP. So what is GSP? At a high level, GSP is a solution that autonomously places services across regions. The idea is that instead of services providing regional level details, we up-level this to a global abstraction and allow users to provide region-agnostic intents in the form of enforceable SLOs. For example, for multi-tenant services, instead of service owners specifying individual region assignments to achieve their latency requirements, a common latency sensitivity intent, or SLO, is provided to GSP for each tenant. Likewise, on the cloud side, GSP places services across regions such that these user-provided intents and SLOs will be satisfied. In the process, we ensure the optimality in the placement, but we also provide flexibility within the bounds of the SLOs defined as well. Furthermore, we also provide experimentation capabilities to our users as well to enable them to evaluate trade-offs between the SLOs they're defining and the overall cost. For example, you can imagine that with stricter latency SLOs, this will require more capacity, and we allow users to experiment with this and figure out what is the optimal point that makes sense for them. To touch a bit on the key benefits of GSP. GSP provides a value of operational simplicity and capacity efficiency for both service operators and cloud providers. For service operators, we reduce the operational overhead by abstracting away regions. Previously, with the high operational complexity, this has caused service owners to over-replicate their service, mainly to ensure there's sufficient buffer. And with GSP, we optimize this to overall reduce our over-replication and improve the capacity usage and efficiency. Likewise, for cloud providers, with GSP optimizing the service placement, this introduces flexibility in the overall capacity management across regions, and this also leads to a more balanced cloud capacity. Next, we'll briefly touch on the key design principles driving GSP. First, as you could imagine, hiding regions is not a trivial thing, and there are many service management aspects we need to consider, such as fault tolerance and routing. To succeed, we need to view the space holistically across multiple service management areas. Secondly, we want to minimize the onboarding costs to our users. The idea is not to rock the boat too much, but rather provide a low-cost barrier to adopt and reap the benefits of GSP. Lastly, infra landscape is fast evolving with various new requirements on the horizon. The goal is to design GSP in such a way that is modular and extensible to be able to quickly support new requirements as they come up with low friction by adopting a pluggable architecture. So with these design principles in mind, we'll now cover the high-level architecture of GSP. In the first step, GSP has a placement planner component that's responsible for fetching all of the necessary information that's needed for determining placement, such as various capacity data, network data, and of course, the user intent. Based on all of these, it will internally compute and figure out the optimal global placement plan. In the next step, this placement plan is then executed by our placement executor, and to do this, it integrates with various domain backends to execute the placement. These domain backends you can think of as backend services that manage the tenants themselves in some capacity pool. At a high level, we provide an out-of-box native integration with various common domain backends, such as the Shark controller in ICSP, as well as Shark Manager. Beyond this, we also support integration with custom domain backends as well, where they implement the necessary interfaces necessary to make this work. During the execution, this deploys a service to the respective regions. Furthermore, we also influence the routing as well to ensure that the routing itself is optimal and aligns with the region placement. Next, we'll dive a little bit deeper, first starting with the placement planner itself. So the inputs to this planner consist of course, the tenant policy, which captures the various tenant placement intents, such as latency SLOs. Likewise, we also gather this input state that provides the additional information needed for solving, such as the capacity available across various regions, as well as how much demand the tenants are receiving as well. This data is then formulated as a bin packing problem, where essentially we're trying to assign traffic objects, which you can think of as items, to bins, which are the regions as well as the resource types available in those regions. This overall solving is achieved by using Rebalancer, which is Meta's internal resource allocation solver framework. We formulate the inputs as constraints, such as ensuring that the demand and the latency for a tenant, for example, are satisfied while staying within the capacity available. One thing worth calling out is that these constraints are also easily configurable as well based on the need, which allows us to iterate quickly as new requirements come up. Next, we'll dive into the placement executor. So after the planner produces a placement plan, which essentially consists of for every tenant of a service, how many replicas and of which resource type to deploy, and also in what regions, as well as this corresponding routing matrix that figures out how the traffic should be routed. Our executor takes this placement plan and breaks this down into a set of moves to get us from the current state to the desired state. Mass, what is a move? A move is essentially a form of upsizing replicas in a region or downsizing replicas in another region. And in this process, our executor provides various execution safety for these moves. First and foremost, it provides orchestration, which is, for example, if we need to move a tenant from one region to another, we will add or upsize in the new region, update the service mesh, before we do any downsizing in the old region to ensure overall safety. Likewise, we also perform pacing in this move execution as well. And on top of that, various forms of validation to ensure end-to-end safety. Next, we'll briefly showcase representative services currently leveraging GSP for global placement. So over the past few years, we have achieved a strong adoption across a diverse and complex set of services. And these range across inference, databases, key value stores, and various index serving platforms. And this list is growing. And with the design principles we discussed earlier, that's powering GSP, this ensures that we are well positioned to tackle this growth and achieve our vision. Next, I'll hand this over to my colleague Yan, who will then cover a case study on GSP.
Thanks, Yatpang. Hello, everyone. This is Yan. Let's now go over a case study of us supporting AI inference. In AI, the latest of AI inference relies heavily on GPU hardware. In short, we need to support thousands of models. They use a wide range of hardware types, and these hardware machines are unevenly distributed globally. We face the immediate challenge of hardware heterogeneity. More specifically, these hardware types are not created equal for the same model. For example, as a later iteration, NVIDIA's H100 is generally more powerful than A100 for most of the models. In the diagram, we can see for the models, the performance ratio is generally greater than 1 between H100 and A100. And across different models, the performance ratios vary too. For example, for model A, A100 is 64% more performant than A100, whereas for model H, H100 can be 2 times as performant, even more. So furthermore, this hardware supply is changing quickly and geographically. For illustrations in the chart, to the left-hand side, we can see that one product team's GPU supply of H100 is sharply increased in August, and some 4 or 5 regions contribute the most for the boost. To the right-hand side, however, A100's growth is apparently limited around July and even dropped significantly in August, possibly being traded back for other product teams. And the regions that dropped the A100 machines are not entirely the regions that has increased the supply of H100 machines. And what we can do to solve this problem? In our solution space, we have 2 key components. GSP, as Yatpang had talked about several minutes ago, is to take the capacity allocation constraints and make a placement plan. ICSP, as a downstream service management engine, is to take the placement decision and materialize it into real infra resources. Let's go over an example for the end-to-end flow. As the input, there are 3 main sources of dynamic constraints for GSP. From top to the bottom, they are capacity supply. It captures which region has which kind of hardwares. For example, region A has 10 A100 hosts. Region B has 40 H100 hosts. Traffic demand, it captures for each of the AI model, what throughputs are required at which region. For example, model X would require 200 QPS at region A, and a lot more of 800 QPS for region Z. The last one is model performance. It captures for each AI model, how many or what kinds of hardware would it take to serve certain amount of throughput. It's kind of like a performance profile. For example, for model X, one A100 can serve for 200 QPS, whereas one H100 can serve for 500 QPS. All the 3 inputs are captured by GSP, and then instead of GSP, it formulates the optimization problem and generates a placement plan. So the placement decision outlines for each model at what specific region, how many and what kind of specific hardware are to be used for serving this model. For example, it decides that for model X, you should use 2 A100 machines at region A and 2 H100 machines at region C to serve for your demand. And it generates this kind of placement plan for all models. This placement decision is then executed by ICSP, which is Meta's service management engine on this private cloud. By the way, we have the past at-scale presentation on ICSP. Please feel free to watch that offline. Now here, ICSP is the common control plane coordinating and orchestrating Meta's infrastructure components, like container management, routing management, auto-scaling, continued deployment, etc. ICSP here will take GSP's output placement plan as its own input, then materialize the placement decision. ICP will update desired states for the AI inference service. For example, it may create a new deployment in region A to host the model X on A100, or it may resize the deployment in region C to increase the number of serving tasks on H100. As the input changes rapidly, the end-to-end flow is continuously running and updating the service deployments. For example, when model Y's demand on region B, to your left-hand side, is dropped from 400 to 300 QPS, GSP may decide to decrease model Y's use of H100 significantly with a slight addition back of A100 to use, and meanwhile increase the model X use of H100 machines. Then ICSP can materialize this plan and update each region's hardware sizing accordingly to serve these production models. By adopting GSP, we see very promising results. We see the reduced number of GPU cores used for the majority of the inference models. It leads to the global saving and the efficient use of these expensive hardwares. And ultimately, this leads to the real revenue win for the company. Okay, that's the end of our case study today. Let's get to Gerald for the takeaways.
Thanks, Yan. The single most important takeaway is that GSP demonstrates that it's feasible to build a global autonomous cloud. It's feasible for not only simple, small services, but also feasible for large, complex, and diverse services. But the work is not done yet. There are multiple exciting opportunities to make GSP better. First, the complexity of multi-region management is growing. One example is the advanced serving paradigms of distributed inference. And second, the management and capacity between inference and the training are separate right now. We want to increase the capacity fungibility so that the same capacity can be used for both in a very fluid way. And finally, our services are using more and more data. We want GSP to support better cross-region network optimizations. And finally, we hope that our talk inspires the community to join us to fully realize the vision to hide regions from service management. Thank you.